Good day, everybody. Thank you for joining us. My name is Armando Berdiel with Lighting Design Lab, and we are bringing you today a webinar about the 2021 Building Energy Code update for HVAC appliances. And it is going to be for both Washington State and the city of Seattle. I can go to the next slide, please. You'll notice that everybody is going to be muted for the time being. However, please engage with us, ask questions, comments, and such to the chat panel on the bottom right hand of your GoToWebinar dashboard. Yes, this webinar is going to be recorded, and a handout of the slides as well as a recording is going to be available at the Lighting Design Lab website, lightingdesignlab.com. At the end of this webinar, there is going to be about a 30-second survey on how we did, how we can improve, how you enjoyed the knowledge sharing. So please answer it after the webinar. Next slide, please. Thankfully, working alongside a couple of seasoned code experts and someone that knows how to meet code with various designs and HVAC applications. So I'll be facilitating, looking to take care of your questions, but thankfully we have these two experts that are going to take us the rest of the way there. So I think, Ben, if you want to go ahead and introduce yourself on the next slide, I'll bid adieu.
When he says seasoned, I hear it as old. So that's an interesting one, but
never.
You know, I'm Ben Roush. This is, I think, third code cycle going, presenting with Duane. I'm a mechanical engineer and a fire protection engineer and a whole bunch of other letters, some of which matter in the energy code and some of which don't. And the most important one down there is I really do geek out on the incentive structure of codes and what are we setting up, so that code nerd is maybe why I get invited back, or maybe it's just because I really enjoyed doing this presentation. I end up having a pretty fun couple hours. I hope y'all do too.
So, welcome everybody, and anybody who's a veteran of these presentations, the last couple of code cycles recognizes this slide. We're by city and state law bound to move forward, and the question is, what's the smartest and most economical way we can make this all happen? So today, of course, is the HVAC session, and those are it encompasses two of the four basic pillars that we built the Seattle code amendments on top of, and the first being that we're moving away from internal combustion buildings and onto clean energy. And then that number three is that doesn't mean we can waste electricity, because we're going to have to take all that clean electricity that we've got and make it stretch far enough to encompass all the vehicles and existing buildings that we're going to have to move over onto electricity in the next couple of decades. I have like an idea that, instead of everybody knowing the entire 256-page energy code verbatim, that you really need to prioritize the biggest deals, and so that would be my personal top 10 list on the left there. That we'll go through each of those and more in this couple hours together. And then on the right, there are still others that need particular attention to their individual needs. We're not going to hit all of those. Just remember that out of that top 10, there's going to be a few that you have to add for your particular building type. So take it away, Ben.
Yeah, so we're going to do some like big picture concepts to start. This energy code is just like every last version of energy code, in as much as it's got a prescriptive path and it's got a total building performance path, also known as an energy model. And then Seattle, Washington at large has Appendix F that can be adopted. We don't know anyone who's adopted it, but I'm sure Duane might be able to list some. And in Seattle, that is adopted into the code. It is in Chapter 4 in C403 for a target performance path. on, sorry, in C402. Never mind, doesn't matter. For the target performance path, basically throw most things out. You're gonna commission your building, you're gonna do some basics, but you get to hit an energy target and they are ratcheting down over time. And if you don't hit it, you get to pay a really big fine. So that's a fun one. Yeah, that still exists. Worth knowing. I don't know that many buildings ever take that path. Duane might be able to tell us exactly how many, or at least a handful of how many.
Some we get one every so often, but it's part of some of the land use incentive programs that we have going, that you need to follow that path to get those height and bulk incentives for your building. So those people end up going the TPP.
Got it. I'd love to read their contracts sometime. Doing some definition of terms, the engineering terms, electric resistance heater, it's 100% efficient. You get 1 kilowatt in or out for every 1 kilowatt you put in. It's good, right? That's good. Gas and fuel fired heating appliances are less than 100% efficient. You get less than 1 kilowatt out. It depends on the device. Old school boilers could be 70%. The newest best tech boilers could be 96%. This boiler from Minecraft, I have no idea what efficiency it is, but it looks cool. Let's go to the next page. What the code is pushing us to, and this is Washington also. If you haven't caught on, I'm gonna steal the thunder right now. Washington State is now a mostly all electric energy code with some notable exceptions we'll do a little later. So heat pumps are where we're going, and heat pumps are grand. Heat pumps do a lot, and heat pumps have historically been disparaged because of something we're going to talk about. So there's a couple varieties of heat pumps. These are simple, single speed. We've known them forever. You know, split systems, PTACs, BPACs, keep going. Let's do the next slide. There's a newer class of equipment out there, and it comes in all the same form factors, but it uses a variable speed compressor that does some magic with the hot gas of the refrigeration cycle, so it'll run down to super cold temperatures without using electric resistance, which, remember, electric resistance steps you back to 100% efficient. A heat pump can be, at peak efficiency, 300 to 400% efficient. We would also call that a coefficient of performance of 3 to 4. So if you hear engineers speak COP, it's really a way of saying it's more efficient than 100%. And that's just part of the magic of the refrigeration cycle, moving heat instead of creating heat like you do with electric resistance and things that you burn. Let's go to the next slide. Oops.
These old ones, we pretty much cannot use those now, right?
Well, some of them you still can use, like the split system still exists. You can still use electric resistance backup in the code to an extent, to a percentage of the total capacity. The PTACs, Seattle's made that pretty hard to use because you get this horrible R factor, which is actually true. Your horrible R value for that area of your wall. So you're back on your envelope chapter. I hope you all talked about that. And I have to confess, I haven't watched it yet.
We'll have a slide on that in about a half an hour.
Oh yeah, good, perfect. Yeah, this one. So this is old single speed compressors, and they had temperature issues. When you got down below 20 or 25 degrees, you hit this heat balance, and you needed electric resistance backup to make up the heat. And of course, you need more heat the colder it gets, which is kind of a pisser. Even with our really well insulated buildings, and the code now, a code minimum building, is pretty good insulation. It still needs more heat the colder it gets. So single speed options, this is the drawback, and then you need a big electric service. But go to the next slide. These are Daikin, but you could get the same curve from Mitsubishi, LG, so on. They have now done these inverter-driven compressor technology that will run down to darn near the coldest temperature you can get anywhere in Washington State, including that more cold northeast corner, without electric resistance backup. So if you're already going to have air conditioning in your building, you already have the power to run these heat pumps. These are VRF, but remember that same form factor, you can get them in vertical package units. Only one manufacturer right now. You can get them in PTAC versions with 2 little through the wall penetrations instead of the big box. And look, even in Spokane, the COP is above 2.5. Another way to say that again is 250% efficient. So heat pumps win every time. We'll show you a graph a little later on how that works for carbon accounting, but know that when we say heat pump, it's no longer this old paradigm that they can't heat, they can't make it, and we need this electric resistance backup, and our service is going to be huge. Oh, geez. Somebody should put in the chat, but hasn't yet, an argument that, yeah, this works for refrigerant, but it doesn't work for fluid systems. And we will talk about that in a bit.
And if you're still got an engineer who says, oh, heat pumps don't work in cold weather once you get below 40 degrees or something like that, thank them warmly for all their help over the years and find a new engineer.
Tell them to pull their head out of the sand. They've been missing out the last 10 years. It's fun times.
So just wanted to emphasize briefly here that you know, I try to spend as little time as possible on the little tiny slices of the energy use pie and really focus on the big ones. But what we're talking about now is close to half of all energy used in buildings, and there are ways we can squeeze that down by probably half. So these are all the big slices that we'll be talking about today. And let me just say a bit about cost, that it is more expensive to build a higher quality, higher performing building, typically, and yet it does get, what we're trying to do is find the most cost effective of all the possibilities we have in front of us at any one code cycle to go for. And we have seen, although it's very difficult to predict and to measure, that once things become mandatory in the code and they become business as usual, it's what all the supply houses stock as normal, and what all the engineers know how to do, then the additional costs for that higher performance do come down, since they're no longer a one-off special idea.
So, you know, if you ask an engineer about cost effectiveness, of course we go straight back to energy and energy cost. But this is from that same Daikin manual. It's now 4 years old. And you can see at design temps, that green line, electric source, VRV, same thing as VRF, the Daikin speak. For most temperatures, it is more cost effective to be running VRF. And this was from 4 years ago. I don't think we could say thanks to Russia for higher gas prices, but gas prices have gone up, you know, wholesale 40% and retail in some locations as much as 70%. So this yellow line is now 40 to 70% higher than it is for gas furnaces, which are just constant across the board. They burn the same amount at any temperature. This is a long way of saying that heat pumps also save money, sometimes save substantial money over a gas furnace, certainly over oil furnaces or propane, and over electric resistance, they're 3 times more efficient. So of course they're more cost effective there. Next slide.
Do have a question, Ben, and talking or very relevant to electric resistance. Question being, can we still use electric resistance heat to preheat the outside air for water source heat pumps, where ERVs are not required, to keep the water source heat pumps at high enough inlet air temperature to prevent head pressure trips?
That is extraordinarily expensive. Extraordinarily detailed question. That's great. It's an expensive way to do it. It would be better to have like a DOAS unit that delivers the air using heat recovery, so you get some of that for free. So just like electric resistance, water source heat pumps can have a cutout temp at, gosh, 45, 50 degrees, and you don't want to walk right to the line because it's got like a once and done freeze stat. It shuts off and then you freeze your space. So the answer is yes, there are capacity limits, and we're going to go over a giant list of must be a heat pump, except we've got a giant list of possible things that you can do, and that's on there for low temperature operation capacity makeup. Go to the next slide. And you know what's interesting? I don't see questions popping up for me, so I didn't know that was there. Thank you. There's a real thing about great, we get an energy benefit. There's a question of who gets that benefit and who paid the first cost. So in things like senior living, I love it because most of the time the incentive structure lines up. The person paying the bills is also the person who paid the first cost to get better incentive, better energy savings, and they have an incentive to get those reasonable things that the code is now telling us we're going to do anyways. You know, energy recovery, ventilation, mostly heat pump based systems. They make financial sense if you're going to hold your building, say, 10 years or longer. We've got the math to show it. And they don't make sense at all if you're a developer who doesn't pay your own energy bills, and that's the tenant's problem. That's a mismatch, and that's why we need a code. We set a floor so that we have to do so well, even if the incentive doesn't line up.
There's one other way to look at the cost issue, and that is that at heart, this is an environmental protection set of rules at the state and the city level that we're like being one of the leaders nationally and sometimes internationally, moving forwards towards helping to put the brakes on the global warming issue. As a side benefit, it pays for itself over time. Developers would rather it paid faster, but that is the bonus prize. You don't get any payback for complying with the Clean Water Act or with seismic safety or something else like that. But energy is the one that you actually do get cash back. Let me just mention what was been alluded to a minute ago, that PTACs and PTHPs, package terminal heat pumps, they have a U value of 0.5 as opposed to the 0.05 something that the rest of your wall has. So we require that if you're going to use that PTAC system, that you have calculated your wall insulation values and accommodated the fact that the 7 square feet of that opening for the PTAC is assigned a heat loss that's 10 times higher than the surrounding wall. So you have to make that balance out. That, together with the fact that you need to get the kind of PTHP that doesn't just shut off and turn into a big toaster oven when the temperature gets below 40, and you'll find that there are very few products anyway. So I'm hoping that we don't see any more. Either we don't see any more PTACs or PTHP units going in Seattle anywhere, or the industry just does a really smash up job and actually makes a much higher performing unit. The other problem with them is that they leak. You know, they're built into a sleeve in the wall, which conducts heat itself, but the sleeve allows you to just pull the whole unit inside for servicing periodically and then push it back in that sleeve. And that sleeve does leak air, even if they managed to make it so it was pretty tight when the first inspection came. It's going to leak air over time.
Can I share a quick thing? We had a East Coast project that the contractor didn't install these well. They got these little flange seals that are supposed to go in that they smushed, you know, they tore out of place. And because it sits in a cabinet that's negative for the VPAC versions, it just sucked air full time so much that the building started raining. Not just humidity, mold growth, it started raining inside, like dripping from surfaces rain. And we smoked bombed one of those VPAC closets, which was really fun, and it just blew smoke out of every seam. So I back you up there.
But people have always loved those because they're cheap. You know, every time you stayed in a really cheap motel, that's what you have for air conditioning. It's the kind that starts roaring when it turns on. So I just wanted to mention, while we're on the topic of the building envelope, that the standards for building envelopes in Seattle, and in fact in Washington State, are very, very strict already. And like I mentioned, we have the air leakage rate now is down to 0.25 CFM from the 0.4 it was before, and And from whatever it was, 1.0 or 1.2, before we had these rules, although I've noticed that many engineers still treat their calculations as though the air leakage rate was the same as it used to be 20 years ago. And now Seattle's got coming up that 20%, or in some cases 35% of your glazing will be triple glazing, which makes significantly less heat loss through the glazing. The question is, are you going to actually, when you do these calculations, believe your own calcs and shrink your HVAC size commensurately? Here's just a quick illustration. The Washington State Code you can see on the left there is typically 30%, and then if you do high performance glazing, you get 40% for any kind of building. Seattle Code now, it'll be different for each building type, but you can see that those are some lower and some higher than the 30%, but that includes the fact that you've got 20% of that glazing be triple. You can get an extra 5% moving to the right under the Seattle Code if you have 35% of your building be triple glazing, and on the far right, if you've moved to being high performance glazing and your 20% triple, then you can get several percent more. So we're tightening up the allowable fenestration area, but giving you more options if you have high performance. You can look. This is looking at it over time. So on the left, you can see that Seattle was somewhat better than Washington State as far as the allowable U values. Then if you look to the 2021 code, you'll see that the allowable U value for the base code is the same in Washington and Seattle. It's gotten better for most of those categories, but then that far right point is that column B, the 20% that's got to be triple glazing or something that's like triple glazing. And then if you want to go for the high performance glazing, you see those red lines on the far right there. Those are going to the typical area for that 80% of your glazing is going to be sort of midway between the triple glazing standard and what's typical. So there are ways to get more glazing that people often want, especially for high-rise buildings, and this makes it a more efficient building. And the question for you engineers is, are you going to actually recognize this in your calcs, or just use your old rules of thumb?
I got to tell you, it's a drop-down menu for air infiltration. It's really not that hard to set up.
It's easy to do, and for some reason causes great anxiety among at least old school engineers. So just note that air barrier testing is not just a good idea anymore, but it's mandatory, and it's mandatory at 0.25 CFM. So let's take advantage of that, because you could actually bump down a couple of equipment sizes and duct sizes when you start looking at this. I had done this table last code cycle to try to like make some kind of sense about, you know, how the HVAC section C403 is organized, and all I can conclude is that there is we've just been tucking things in wherever it seemed sensible for decades now, and it's just kind of a mess. So I'd advise having something like this printed out and put in your table of contents to be able to help find things in C403, because there really isn't any discernible logic there. Uh-oh, but now we got a flow chart.
Yeah, I'm an engineer. I love flow charts. If I could have figured out a way to make those Windows slides that Duane just did a flow chart, we would have a flow chart for that too, but I actually can't figure it out. Doesn't seem to be a way to do it. So we're going to talk a bunch about the prescriptive path now. We're going to talk about the total building performance path a little later, and we're not going to talk that much about the outcome-based energy budget, that just show me throughout the code path. I wanted you to see all of the things, and it deserves a flow chart because there's all these occupancies that do all these things depending on if you're a B occupancy and you're this but not that. One of the things I just love about the most recent version of the code is it's clarified that medical office building is office building. I didn't know it wasn't until it came out and clearly spelled it. I love that. We're going to say dedicated outside air system, DOAS. We're going to say it, I don't know, another 15 times. And we're going to say TSPR, total system performance ratio, at least another 5 times. So keep those in your mind. It is worth saying that C403 has a, oh, go ahead. Yeah.
You want me to go for it?
Yes. C403 has a bunch of small changes around the edges. The biggest change in Washington is that we are a nearly all electric code. We're going to show you exceptions to that allow you electric resistance or gas. But the other biggest, like for me, 2 hands in the air, we have a table for heat recovery chillers. We have inefficiency standard. We moved to SEER 2 for equipment, which is what most equipment is coming as rated now. So basically we get an update that matches the equipment we can buy. Pretty exciting. There's some very specific rules about if you're really big boilers, which again, you only get to use in a couple places now. There's some carryover from what was in the Seattle Energy Code last time has moved over to the Washington State Energy Code. But if you're working in both jurisdictions, none of those is going to be a surprise or difficult to do or even difficult to detail. You'll already have those. The other big thing that the C403 is setting up for is the ability to switch from a high temp system to a low temp system in the future. So boilers right now, conventional boilers run 180-degree loop temps, and heat pump water heaters or air to water heat pumps, or take your pick of what terminology you want to use there, really like to run at like 120 degrees. They can maybe hit 140 degrees on a design day on the coldest day in Seattle. They're not going to get there in Spokane. We do have new best options, and honest to goodness, I get a new one once a month that is a new chiller that runs down to some new lowest temperature for heat pump mode. And it really is exciting times because it's ever constantly there. We now have one that will run down to 5 degrees, which is much colder than the Seattle design temp, 5 degrees at full capacity. So we can do hydronic systems also. That was the question I said somebody should ask me back when. So when you're replacing terminal equipment, you're going to replace it with a coil that can handle 120 degree and takes a higher delta, basically a bigger coil, so that you're ready for the future.
Ben?
Yeah.
The new spiffy one that can run down to really cold temperatures, what kind of temperature water can it produce? Because I've been just hearing rumors about a new one that's hitting the market that can produce gas boiler type temperatures.
Yeah, they say it can do 180 down to 20 something degrees, and it can do 140 if you're running like replace a condensing boiler, would often run at 140, 120 return, 140 supply. It can run 140 down to like 5 degrees. I don't know if we're allowed to say brand names here, are we?
Well, we typically are, but that particular brand, I had to like swear secrecy when they finally told me who they were and what they're up to. But just all of you in the listening audience, be aware that there's a product that's going to hit the market soon enough that there are already engineers specifying it for projects that is capable of providing hot water at the temperatures that you get from your gas boiler, which means that if you're doing a changeover for an existing building, that you would not have to go in and upsize all the coils in the entire building. You'd actually be able to use the same coils and piping that you have otherwise, which is a game changer.
I was going to mention for Duane and Ben, and I think leaving it there is perfect, but if we do mention manufacturers' names, there will be as an example of technology, not an endorsement. Yeah. There are some questions on the chat saying, what does it rhyme with? But I don't encourage us to answer that one.
You'll have my contact information at the end. Email me. I'm happy to share. I can't endorse it because we haven't used it in the project yet. And we have a solid, firm rule that we will be the second one in town to use the technology, not the first. But it's CO2, supercritical CO2 based. It as a refrigerant. We're going to talk about refrigerants later on. So it's pretty neat. It's pretty exciting. Something Duane said, I want to make sure it's super clear. All the mechanical engineers in the room might be raising their hands about this one. When you replace with a different temperature system, you have to replace the thing making the heat, the boiler, the heat recovery chiller, whatever. The coil on the other end needs to be resized because it needs more fins for that lower temperature. It needs more area. But the piping in the middle, as long as you didn't change the temperature delta between the supply and return, the piping gets to stay as long as it's okay. Investigate your piping; it might be falling apart. So that's sort of one of the magic of hydronics is that you get to keep the pipes, the pump. You might need to replace when you replace a boiler with a heat pump chiller. You might need to replace the coils in the building, but again, we're getting better options that maybe you don't. A lot of coils were already oversized. If it was sized at 180, but it was 50% too large, your 160 supply might get you there. Talk to your suppliers. All right, I'm done with that.
Data centers, just want everybody to know who does cooling systems for data centers that we've now referenced the 2022 version of 90.4, and we and chapters or sections 6 and 8 in particular. It's not a huge change from the 19 version, but make sure you're on the right one.
Got to find that mute button. So I think it's really important to understand what is a data center and what is merely a computer room. So that's power density, and that's of the room. So you might have a server rack that tops, they're now topping like crazy watts per square foot, like 100 watts per square foot. But the room could also, if you're a computer room, could have post racks, could have random other equipment, could have a UPS that really doesn't put off that much heat. So in the room, you got equipment load and a power density that makes you a data center or a computer room. So this is straight out of definitions. It's worth saying that 90.4 does a change in how we measure power, and it focuses only on HVAC and energy. There's an older metric out there, the power usage effectiveness, the PUE, that doesn't really apply here anymore. So worth getting in there. If you do data centers, and look at the definition to make sure you do data centers, there's a fair amount that goes into that, but it all comes out actually to a pretty easy efficiency, electric use per capacity unit.
So the dividing line between data center and computer room is 20 watts a square foot.
And 10 kilowatts, yeah.
Ben and Duane, we do have a question about the previous slide. Someone mentioned that they saw, before that one, sorry, that they saw a requirement for demand response on certain boilers, and I wanted to ask if you'll be addressing it later, then we can leave it for later, or if you're not, if you want to address it now.
Yeah, so the demand response, that's required demand response signals to slightly set back heating and cooling. So this is in C403, but we're also going to talk about it in C406. So if you're the right type of system, you could be required to set back room set points on a demand response signal, but you could also be required to set back, this is talking about loop temperatures. So you'd make your chilled loop slightly warmer, or your boiler loop slightly, if you're a heat pump based boiler, slightly less warm. So it's there, but it's only on really large systems. I don't remember the threshold. I have to go look it up. Contact me after if you want to geek out on that further.
All right, we're into TSPR land, total system performance ratio. This is instead of only looking at HVAC systems by the efficiency of each fan and chiller and boiler and everything else in the building, there's a total system performance, which is like the little formula at the top there in white. All the heating, cooling loads at the coil divided by the carbon emissions that were from that electricity, and you got to be better than one. So it applies to those building types you see up there in yellow on the top right there, and we actually have the rule set copied into Appendix D if you just really like punishing yourself, but PNNL has posted a calculation tool online that's free, and that I've heard from all the engineers that have used it that after the first time you've gone through it, it's pretty easy to use. And whereas a building energy model might take, say if it took you 5 days of work to put that all together, a full-scale Energy Plus model or something, this is more like 3 or 4 or 5 hours. So just this table is in the Seattle code just to make it easier than the code requirement looked in the state code to understand which things are and are not required to do TSPR. Now, last code cycle, they were just guessing what this would happen, but I guess now you're not guessing anymore. Is that right?
No, we're not guessing anymore. We've got many projects that have needed to do this. And we know pretty well what's going to pass and what isn't ahead of time, and get to have those discussions way back in SD when we now know to do these, because we got caught the first couple doing these like 60% CD or 90% CD, and it was too late. It was a problem. So it's worth saying that list of occupancies Duane showed in the last slide is pretty much a direct overlap with what requires dedicated outside air systems. So you already have an energy efficiency that reduces your loads a great deal. And remember, it's heating and cooling loads over carbon impact. So the only time we've had a new building get in trouble is when it's been primarily gas heating based, or when we tried to do the crazy, enhanced VAV pathway to get out of DOAS, which we have only done once, and we ended up taking it back and going back to DOAS. So this is really a backstop on new buildings. The chances are quite good, now that we are mostly heat pump based in Washington State, the chances are quite good it's going to pass. It is not the same truth for existing buildings. So realize that Chapter 5 in existing buildings points you back at Chapter 4 and says, do all that stuff. There's no like, don't worry about TSPR written in Chapter 5. So when you get back and you do the TSPR on an HVAC only upgrade, we have had those fail fairly often. We have needed to do other things to the building to reduce the heating and cooling load. Or we have needed to switch from a gas system to a heat pump based system, which I'm going to show you why that carbon works out here in a minute, but just trust me, it works. So if you're an existing building, you need to push your engineers to do this right off the bat, and it's easy. Duane said it, it's like a couple hours. It's not hard or long. Duane, I'm getting an echo from your computer. Weird, and it just started.
Well, I'll just.
All right, you muted. Anyways, it's not hard or long. Honest to goodness, you can do one of these in a couple hours on a moderate, 50,000 square foot building. It's big box modeling, and the PNNL tool is truly grand. If you haven't checked it out, you'll need a login, but other than that, it's pretty easy. The rules are there. You could build that energy model, and I don't know why anybody would ever bother. I think that's grand. Let's go to the next slide. So TSPR, again, heating, cooling loads over carbon emissions. This is an important thing to know. The factors are different units in the, C407, but it uses the same factors for TSPR basically. And so I converted them. If you do electric and you convert it to therms, it gets to 20.5 pounds per therm. You can see natural gas is 11.7 pounds per therm. And it's a sad truth, I'm going to show you in a minute, that our electric is at least as bad as gas for electric resistance, maybe not this bad. But you want to set up an incentive structure. Heat pumps will win in every scenario. If you're having trouble with TSPR, put more heat pumps in your design. Hopefully you did it at SD like I just said, so that you have time to put them in your design, hopefully. Let's go to the next slide.
And
so this is—
don't really even have much of an option to do something other than heat pumps anymore, do you?
You don't really. And again, we're going to show you that exception list later on. But yes, you have very few options to do electric resistance and even fewer to do natural gas. Okay, so this is from the eGrid. If you just Google the EPA power profiler, you'll get here. You can pick the grid we're in, which you'll note is many, many states, not just Washington. So if you pull an electron off our grid, you're also counting, you know, Nevada and Utah and so on, their grid. So great, we got the CO2 per megawatt hour, 639. The new 2021 numbers just came out. And it's 634.6, so it's nearly the same. It's basically unchanged. The mix actually changed a little. Hydro was actually down, and natural gas was up in our overall grid, which was an interesting move. Anyways, if you look at, go ahead to the next slide, future CO2, we have a Washington State passed bill several sessions ago that puts us on track to oh, we cut the text off the bottom there. Funny. It puts us on track to be a net zero carbon electricity. And it's important to say it's net zero. It's not zero carbon, it's net zero. It needs offsets, so it is possible. Let's go to the next one. Being an engineer,
wanted to interrupt before you got to the chart, if that's all right.
Of course.
So someone asked for clarification on the standard unit for the TSPR, if it would be kilowatt hours or kilograms of CO2 emitted, or what is that unit?
It's a good question. So you actually compare your building's heating loads, cooling loads over carbon emissions to the standard design, which the PNNL tool completely does for you. It's done automatically. You don't build a standard design like you might as an energy modeler. And you must be better than the standard design. So its units would be BTUs per carbon, you know, pound CO2 or kilogram CO2 or metric ton CO2. I don't actually know what the carbon emissions metrics are, and it doesn't matter. You get a TSPR that says you've passed or not. Like you get a report that says I passed or you didn't beat the standard design. Again, mostly existing buildings that need to worry about that. I hope that answered it.
It is a ratio.
It is.
And so it just has to be better than one. And that's the ratio. And that's what you're gonna, and so at that point, it's unitless.
Right, yeah, it's true. So it's your proposed building over the baseline. So the units all cancel out in the end. Quite right. Okay, let's go back down to that there graph. So engineers, we like graphs. The blue line is the carbon of gas, and that's straight out of that table I showed you from the code. If you actually look at boiler efficiencies, that's not what you get. You only get 80% of it, the orange line, or even the best, 96%, that gray line. And they get worse over the life of the boiler. Then you replace them, you go again. The yellow line is electric resistance, which again, as we fall to that 2045, no, net zero carbon, can't say no carbon. Off you go. That line's going to fall with it. The blue line way down at the bottom is heat pumps, which again are 300%. This one assumes a 300% efficient, COP of 3, but it could be even more depending on the technology. So you can see again, heat pumps win, straight from the last slide. Electric resistance is just now crossing the line where we can say definitively it really is better than all gas options. It is only occurring maybe next year. And in the future, it will be rapidly much better than any gas option. I think that's it. Duane, sorry, you're muted now.
TSPR was fun. DOAS, our next 4-letter acronym, is just as fun. Dedicated outdoor air system. This has been around for I think the 3rd code cycle now for DOAS. It's required for those occupancies you see at the top there, which as Ben said, resemble strongly what's in the TSPR. These are, and what they have in common is that they don't have large process loads like restaurants and hospitals and laundries, so forth, that have grocery stores that have big loads. So you gotta, in Seattle, we add dwelling and sleeping units that if they're a central system and not individual units. And we add the corridors and common areas between dwelling units. One bullet point there is that an accessory occupancy, which defined in the building code is less than 10% of the floor area of a particular floor of a building. You don't have to do a separate DOAS if you've got, say a big warehouse with a little office area in it. There are a couple things to note there. Those last couple of bullets is that fan power is limited now to 0.8 watts per CFM. I think that came straight from a California code amendment instead of it was 1.0, right, Ben, before? So we're clarifying that you can temper air on the DOAS up to as much as 55, or cool it only as necessary to dehumidify. Also, just there's been a lot of confusion about Group R for Seattle code here. It's excluded at the state level, but Seattle's got it in there, and we're clarifying that if you're served by a central system, then you are included for that for those requirements, and the common areas are, but otherwise, if you're doing the little individual units, then you're exempt. Yeah.
Yeah, let me say a thing about residential for a second. I feel, in my energy saving heart, feel a little stab every time I get up on the roof and there's 100% outside air unit without energy recovery in a residential. It's very common to just pressurize the corridors. And it's a slightly larger unit and a second return duct, and I can show you energy model after energy model where that has a 7 to 10 year payback, and that is actually borne by the building owner. So it's just good money to do, even if you have a way around it by not making any central units and so on. I want to speak the special occupancies. These A3 occupancies are weird ones because they are, they're full of people and then they are completely empty. So for DOAS, it's got to have this ability to ramp up and down by, if you do the 62.1 ventilation calc, the area and the people, you get two different numbers, and the area is what you got to do full time, and the area plus people is what you have to do when it's occupied. And a lot of these also have like CO2 based controls. It's really hard to pick a unit. If you did it with one fan, it almost can't be done. So the magic is, you can't call them fan walls because I think that's trademarked, but fan arrays, where you do a bunch of little fans that are flexible. They're more flexible for flow and pressure. And they also take less floor space, so architects are happier with their mechanical engineers. And they use less power overall, and they can be driven off a single VFD, so you're not buying a bunch of little VFDs you got to maintain. So in general, we're going to be looking to more and more of those when we get into these oddball occupancies, and it's because you have to be able to turn that unit way up and way down, because all it is an outside air unit, and the outside air when you're not occupied is pretty teeny.
Imagine that. Systems that go off or turn way down when nobody's there to use them.
I know. Crazy.
We need demand control ventilation for these spaces like that are ramping up and down. You need them for for any of these things that I've detailed in the first couple bullets. So when we changed that occupancy, if you know the mechanical code chart that says how many occupants they assume per 1,000 square feet, which is, by the way, different from the one in the building code. We brought that down to 15 last code cycle so that it would include retail. If you can just picture, your typical Macy's on December 15th compared with your typical Macy's on February 15th, there's an enormous difference in occupant load in those places. So that really worked out. There are a number of little occupancy types you can look up that don't require this, that theoretically have that kind of occupancy level, like if you've got a nail salon or something like that. And then there's these two exceptions. Ben, do you want to describe these, or do you want me to try?
I think I can try. So if you're teeny systems, as in let's say we've got a teeny city hall that just has a conference room, and well, you'd have office next to it. So this is a poor example, isn't it? Stick with it. Conference room, and that's all that you need a DOAS for in the building. You might not top 750 CFM or 1500 if you get a more effective heat core. We're going to talk about what that means in a minute. And then the multi-zone system with design occupant component outdoor flow less than 100 CFM. Yeah, that's a thing unto itself. That deserves 4 slides if we're going to try and explain it.
It's 100 CFM per occupant they're talking about, right?
Right.
And so what do you have examples of what kind of spaces use less than or more than 100 CFM per occupant?
Per outdoor airflow, I'm trying to think of anything where I actually come up to 100 CFM of outside air it's usually high exhaust spaces, right? Where it's more like makeup air than outside air, but I still need it, right?
Mm-hmm.
I don't know. I want somebody to put it in the questions if they got an answer for that, because I don't have one that out of 62.1 that pops to mind for 100 CFM. Something with a giant restroom core.
In any case, we thought that it was important enough that we put this exception in the code there. So
you have a question on that one, or someone seeking clarification? Excuse me. And the question goes, for those res buildings, if a central DOA serves both dwelling units, it's also required to serve corridors, amenity spaces. But if you have in-unit ERVs that serve those dwelling units, a DOAS may not be required for those corridor or amenity community spaces.
No, the common areas still require No, you're right. For the DOAS, that's true.
If they have the in-unit ERVs for the dwelling units, a DOAS may not be required or would not be required for those common spaces.
I think
I
that's
thought they stood apart. I'm gonna go look. I'll answer it back in the chat.
I appreciate it, guys.
All right. So if you've got, you need to have an economizer. If your DOAS is either on the roof, or out in the garden, or it's adjacent to an exterior wall or roof. So we made this exception that if your chiller is buried deep inside some interior room, then that would not require economizer. But now that most new construction is going to need to be heat pump driven rather than having separate chillers and boilers, I'm not sure if this is going to be relevant any longer.
Oh, and I got the answer for what would require 100 CFM per person. It's really weird ones, and it's mostly really air exchange based. So it's prison cells, nail salons, barbers. It's things where it's really more about dilution of air than true ventilation.
Okay.
where the exhaust rate would drive you up.
So if you're
But I
doing
haven't
an,
gotten back to DOAS yet, so I'm going to have to answer that at the end. Maybe I'll look it up at the break.
all right, DOAS
All right.
demystified.
Yeah, so we did this in the last version. This shouldn't be a surprise to anybody if you've been watching these in the past cycles. But the difference between what we conventionally would do for an office building way back, like a VAV system, you would introduce to the return air path, you pull it out of space, you'd pump in outside air, you'd mix them together, you'd reheat or recool that and put it back into the space. So you're essentially using air to move a bunch of energy. And that outside air mixing in could be good in some cases, but could be bad when it introduces like more humidity than you want. You can't deal with it directly. Now you're dealing with it in a much larger airstream, things like that. Let's hit the next slide. So the only difference between what we used to do and what we do now is that we introduce outside air through a separate unit separately into the conditioned space. And that's important to know. I still see some people trying to plug, like when we do like a code review, trying to plug, outside air into the back of a fan coil, and that's no longer allowed. You need to put it directly into the space. But that's it. That's the difference. Instead of mixing the return and the outside together, we deliver it separately through a separate unit so we can do the conditioning. And importantly, go to the next slide.
Well, so just to review, that's the traditional method. Outside air and return air combining and then going into the VAV, right?
The one we did for the first 15 years of my career, and here's what we've done for the last 5.
All right, and now next.
All right, the important thing that gives us is the ability to heat recover. So if you take your exhaust airstream, if you're putting air in, you've got to take air out of a enclosed space. You can take your exhaust airstream and you can get heat recovery out of it. So you can get the heat, you can get the energy. Let's go to the next slide and talk about the difference. And I'm also going to show you some psychrometric charts. I know you're very excited. On the left is an energy recovery unit that is most often done with an energy recovery wheel, also known as an enthalpy wheel. We could just keep going with the names on that one. But it spins around between the exhaust airstream and the supply airstream, and it picks up both heat and humidity, or for the mechanical engineers in the room, sensible and latent heat. And it moves it. So in the winter, you get to pick up inside air heat and humidity and put it back on outside air entering. So you get to pick up heat and humidity right when you want it in the winter. Conversely, in the summer, you get to take that cooler, drier air from inside, roll it back around into the outside airstream where it cools and somewhat dries, although in Seattle it does less of that, the airstream. So we get this question all the time, what about the air leakage, right? Because there's got to be some air leakage. And 62.1 has handled this. They have air classifications, and I'm not going to get too deep into this. But for things like restroom exhaust and just general purpose relief return exhaust, you're allowed to have 10% leakage to the supply airstream. And that air is primarily an odor concern. There's no real like toxic health hazard concern. So you're allowed to have a minor amount of air leakage. That's the maximum, right? Hopefully you get less. And there's little blade seals that keep too much air. So it's really only the air in the core that gets leaked around. Oppose that to the one on the right, and this is more like a lab style energy recovery unit. So that one has a heat recovery core that only does heat, only does sensible for the mechanical engineers in the room. And there is zero leakage between the exhaust airstream and the supply airstream. So if you've got like class 3 or 4, like not okay to leak air, you can use this and still get a pretty good heat recovery. So
Ben, I had someone ask me for clarification on DOAs and economizers.
yes.
Question being, when economizers are required for DOAs, do we really need to consider bypass requirement?
Yeah.
And if not, could you explain exactly what an economizer requirement for a DOAS may mean?
Yeah, when we first saw this, and they appeared to be conflicting, because when we think DOAS, we do not think economizer. So economizer is the ability to turn to 100% outside air. Basically, all of your supply airstream can go to outside air so that you get quote unquote free cooling. So if it's 65 degrees outside, but you got a good solar load, so you definitely need cooling, you can do it with outside air instead of turning on your chiller or your compressor or whatever is doing your cooling. Now, in a DOAS unit, you don't have all of the airstream. You have an indoor unit doing its thing, and then you have an outside airstream. So the economizer only works for the outside airstream. And I'm getting lucky here because this one on the left has these teeny little dampers above and below that giant orange wheel. Those are economizer dampers, bypass dampers. So you can stop the wheel and you can bypass the core, and you can just sit there and push outside air in. And there is like a 10-degree, it depends on humidity as well. There's like a 10-degree band where it makes sense to do this, but it is an energy benefit over cooling that air. So the economizer is on outside air only instead of all of your airstream. That's very confusing. And you need pretty advanced controls. You need temperature and humidity on outside air, supply air, and return air, the exhaust airstream, to know if it's a good idea to turn on your economizer at any given point. At least in the enthalpy wheel, the energy recovery version. In heat recovery, you can do it on temperature alone because it's sensible alone. Let's go to the next slide. I know that you're super excited to see a psych chart. I am.
Is that like 58 to 68 outside air temperature or what?
Yeah, it could be. So if you're cooling to 75, this is a very much an it depends answer, but you might get away with up to 70 degrees of economizer of outside air, where it was a benefit over just exchanging with that 75-degree air inlet. So if you're cooling to 75 and most of your building has gotten to cooling where you'd want to use free cooling, your exhaust airstream is 75, and your incoming airstream needs to be something less than 75 to get the cooling. So it depends on where you are in your cooling and how much each individual zone is ramped up into cooling to actually need it. But you probably are not going to cool that air down, particularly given that we've given a DOAS tempering limits. They can only cool so far and heat so far. So that's really your threshold for like a sensible version. On a energy recovery version with humidity weighed in, it's got like error bars to it, kind of. So we only get to heat to 55. We'll probably want to we'll want to keep energy recovery all the way up, but we only get to cool to, is it 80? I'd have to go look that up. So we would be using free cooling to 72 maybe, and below 62, you're probably going to keep using the energy recovery. You don't want too cold air moving into a space. The likelihood that it's 62 out and you're really ramped up and cooling, you'd need a huge solar load or huge people load.
All right, suffer here.
Yeah, psychrometric charts. I'm going to do a brief intro. If you haven't seen them, they're how air works with both sensible and latent put on the same chart. So sensible is along the bottom for temperature, latent is along this curvy axis on the left, and it's wet bulb, dry bulb. Relative humidity are these curved that go from like low to lower left to upper right. They kind of follow the curve of the wet bulb. So on a sensible, on a heat recovery unit that's sensible only, you can only move left and right on this curve. You move across relative humidity. You don't get any latent recovery at all. If you've got latent heat to recover, too bad, you don't get it. You only get the sensible part until you start condensing on the heat exchanger, which isn't always appreciated by your manufacturer. Then you get some latent. Let's go to the next one. Oh yeah, I should have said this too. So this code updates the requirement from 60% heat recovery to 68% heat recovery, and updates from 50% energy recovery to 60% energy recovery for Washington State, and Seattle already had 60% energy recovery. So this is the energy recovery version, and it works on enthalpy over here on the left. So your energy recovery, your total energy recovery at 60% can be rather more advantageous than your heat recovery at 68%. So even though it's 8% more, your heat recovery can, in total, do less for enthalpy for you, for the total energy recovered. So that's why you get different thresholds for sensible or for energy versus heat recovery. And you need to be really careful with this stuff. You need an engineer sitting in the room when you start talking about 60% energy recovery. I've given some examples of where you might be kind of worst possible case for Seattle for cooling, where you're 75 inside, 95 outside, and really humid. This doesn't really occur a lot of the time in Seattle, but it's a worst possible case I could think of that I've ever seen ever in Seattle. Even on the other side of the state, when it gets warm, it doesn't get that humid. So the energy recovery tends to cost more some of the time. And it's a question of whether it actually benefits you. And the only way you can answer it is by putting it on a psych chart or putting it in an energy model. All right. Oh, one more thing, I'm sorry. That 68% means that we got 68% from the hot line to the cold line in heating. And the 60% means we got from 60% of the way from the hot line to the cold line in heating. They're both rated in heating. You'll get different values for heating and cooling. It's rated in heating. The Seattle Energy Code in the past version had a delightful informative note that showed you the exact math, and I suggest you read it.
Delightful, huh?
It was too.
So this is something from last code cycle, and that's that apartment units can no longer use the trickle vents plus bathroom exhaust fan to ventilate. It turned out that that never worked in cold weather for tall buildings, and in the when we have a wildfire smoke week, that can, which I heard we might be getting some tomorrow here, that also is just miserable because people were kind of faced with having to either have no outside air or have outside air with smoke. So anyway, you got to have mechanical ventilation to each habitable space, which is a living room or a bedroom typically of a dwelling unit. And we've actually got 67%. We tried to get some things fixed for sensible heat recovery, but it's still 68 in the Washington Code. I'm not sure if that's a different piece of equipment or not. DOAS, balanced.
Yeah, so in the last cycle, Duane asked me to critique some of these. So you can go individual little suitcase units like Duane just showed, but you got to get into every closet and change the filters twice a year. Maybe that's fine if you already have to be in that unit changing filters, maybe not. The rooftop units, it eats up some rentable floor area because you got those shafts coming down, you got fire dampers, it's got some complexity to it. But the thing is to live on the roof, which might be mostly otherwise unoccupied space, except for that 40% solar set aside, of course. You can do it floor by floor. We like this a lot, but it does still eat up some rentable floor space, and we got to talk about what height in the corridor is really an acceptable height. You know, can you fit your king mattress down that corridor endwise instead of the other way? It's really important. But you get to avoid some of the complexity of like fire dampers if you aren't penetrating firewalls. So there's a bunch of different ways to get this done, and it depends on your building's form factor for exactly the best way. But in general, I said this before, it's going to have a 7 to 10 year payback. It's good energy. The only downside is the tenant benefits this one. So for the building developer, if you're individually submetering tenants, you got to find a way to make the value proposition like, look how low your energy bill will be if you live here, and I get to charge you a little more for that. That's the only way to make that value proposition.
And our state law says that it's cost effective for owners and tenants. It did not say it's cost effective for builders and developers necessarily. So this slide is not much changed from last code cycle, except that underlined thing at the very top that the state picked up most, like 90% of what was in the Seattle code last code cycle to make it required statewide to go to heat pump space heating. You see there's a whole raft of exceptions. You know, there's what I was calling the passive house rule, that if you had a very limited amount of overall heating capacity per square foot of building, that could be electric resistance, that you're allowed that 750 watts per room of electric resistance for an apartment or a hotel room, and 1,000 for a corner room. We added one little thing there, that second bullet under item 2, that if you have a room that's at an exterior wall, but it doesn't have a window, that can have a really little heater in it. But otherwise, we got a whole bunch more that relate to mostly to either very small loads or very occasional loads. If you have to do a pasteurization cycle, you know, that's very not often, or for loads that just come up when it's very cold outdoors, you can have some additional electric resistance. But notice that none of those for Seattle permit gas.
Yeah, I'm going to show you a similar list in a second, but answering that question from before, water source heat pumps, you get freeze protection. You know, that's lockout protection. So there's something there. The systems look exactly like what I showed you before. Airside systems we can use, split heat pumps, mini splits, VRF, VPACs, PTACs, only the nice through the wall with the 2 little hole ones because we can't make up the UA otherwise. For larger systems, next slide, we can do exactly like what you've seen, you know, in larger hydronic systems. Centrifugal chillers can act like heat pumps with the right valving. Heat pump chillers are becoming just a standard of how we do things on the Seattle side. On the other side of the state, we still need electric resistance backup for these, and I'm looking forward to the near-term future in the product development cycle where we don't, and then we start having the discussion. Hit the next slide. This is the big aha, but your boiler over here on the right, this is from a life science project that we are just getting done with design in Seattle. We were not allowed to use boilers or much electric resistance, nor did we have the electric service to do it. The chiller, the heat recovery chiller, to make air to water heat pump, same thing, to make the same capacity as a boiler. You can see the size comparison now. 4,000 pounds, about 8 feet long, 17,500 pounds, and 43 and some feet long. So there is a size, electrical, structural, keep going impact to making these choices. And still, with where gas prices are going, if we do a life cycle cost, it's going to pay. It's great. If we do simple cost, it's going to pay in 8 to 10 years on this one. It's still good math to do it.
So this is for a heated only space. If comparing the heat pump system to a gas boiler and a chiller system, it's a lot closer as far as size and weight, right?
Yeah, this building's kind of a crazy one because we have an air to water heat pump, but then we also have a chiller plant because it's life sciences. So we were going to have a chiller plant no matter what. This chiller doesn't get to, it helps the chiller plant, but it doesn't make up the chiller plant. But this is, again, that's an oddball. In a standard office building, you could do a 2-pipe changeover, so you're not running 4 pipes, savings, and you can run your chiller in the summer for a chiller, and you can run it in the winter for a heater, and you don't have double the equipment. So Duane's point is valid, occupancy dependent, but talk to your engineer about what you're going to need to do for this. Duane covered this pretty well. The language here, if you go actually read it, this is from Washington State Energy Code. For the purposes of this section, electric resistance HVAC, HVAC heating energy shall not be provided by electric resistance or fossil fuel combustion appliances. That seems pretty unambiguous, but hit the next slide. Then there's this giant list, just giant list of exceptions. And it's climate zone based. So climate zone 4C, which is to say west of the mountains, and climate zone 5B east of the mountains, and the little bit of 6B we have is just honorary 5B. You get exceptions based on what climate zone you're in. So know your climate zone. But you can use fossil fuel heating in a lot of places on the east side, and you can use electric resistance in places where it just doesn't make sense. Heat pumps don't do it well, or they're just not there yet. You can now get heat pumps for kitchen makeup hoods, and it's really nice because you have a cooled kitchen, which is really delightful for the people working in it. And it's really capacity limited right now. It's got issues, like pasteurization, you really can't do with a heat pump. It doesn't get hot enough fast enough. So these are really reasonable exceptions. Something that's super fascinating, go to the next slide. And I don't have a past precedent for where the Seattle Energy Code has more exceptions than the Washington State Energy Code. But in Seattle, you actually get they cross out climate zone 5 because Seattle's not in climate zone 5, but you get a bunch more exceptions in the Seattle version, including, some things that I think are fairly clear, like emergency generators. I thought that was pretty clear that it was off the board in Washington. So I thought that was an interesting add.
Yeah, and this is our Seattle process, as painful as it is, grinding along for 2 years to come up with this code. People came up with, at the very bottom on the left, wastewater heat recovery auxiliary heating. It's one of those things that really needs this to clarify that yes, it's okay. Emergency generators were already allowed. Now I think we also allow some fossil fuel for emergency space heating for those essential facilities. So things come up, and these things probably make themselves make their way into the next version of the Washington State Code.
Ben, have actually a couple of different people asking for some clarification on the building that you're working on, their design. I'll pick this one. For that life sciences building slide, was the heat pump the larger system or the smaller system? A couple of people having that question on.
System. So we don't need nearly, in life sciences, like they've got a vivarium, we don't need nearly as much heating as cooling. We've got a big cooling load. It's to the extent that we did our heat recovery by putting a heat recovery chiller in the exhaust plenum. Like that's the level of extra heat we have in that building.
Thank you for the clarification.
All right, simultaneous heating and cooling.
Yeah, so this is in your thermostat section, and this runs against traditional engineering practice, which has always believed in heart of hearts that there's a magical barrier 15 feet inside from the window wall of a building, and that outer 15 feet has its own little heating and cooling system, and the inner part of the building has its own in there, and they stay separate. Since that actually has some problems with laws of physics, that we're not letting you be simultaneously running heating in the perimeter and cooling in the interior of the same space. And so you can have one be heating or one be cooling and the other neutral. You see this opening here between one space in a building and another larger space. If that opening is bigger than 10% of the floor area on either side of the opening, and it's a permanent thing, not closed by doors, then that's a single space as far as that simultaneous heating and cooling thing. You would think that this wouldn't be something we had to work on, but we're fighting a couple generations of tradition in mechanical design.
Yeah, and I'm 20 years into my career, and I'm kind of surprised we're still talking about this, but here we are. I wanted an example of what would a 10% of floor area opening look like. And so if you go it's actually cut off in this. But if you go look, and this has like a medium pressure distribution with VAV zones inside and outside. This was common in VAV systems. I gotta say, we're building more and more floor plates to meet the daylighting requirement to get the higher, higher glazing and do zonal controls. So that our floor plates have stopped being these giant rectangles that need an interior zone and an exterior zone, or we're handling it by putting radiators along the perimeter, and those can be cast down, like a cast cavity in the, they don't have to be like out seeing radiators. So there's ways to handle that allow you to not deal with this, but dealing with it, it's primarily a controls and commissioning issue. And our commissioning group really hates it when this happens, because you have to not only check that this thermostat does its temperature change and does what it's supposed to do at its zone, but that the other one that's linked to it that's an internal zone also goes up and down with it. So it's an easy thing to miss in commissioning. It's a bit of a pain to program for the controls folks. And for the most part, we don't build giant floor plate buildings anymore, and it's becoming less and less of a concern. Oh, well, and our window envelope is like only 40% now, instead of this giant, beautiful glass wall that honestly makes me uncomfortable. It's so much glass.
Yeah, that it's one thing to look that we're limiting the overall amount of glass. We've drastically limited the leakage through the wall assembly, probably by a factor of 4 or 5 from what it was a couple decades ago, and improve the overall U value of all these components significantly. And so what used to be where you had to have some people would put a blanket over their lap or something like that if they sat next to the exterior wall, now you shouldn't feel much difference anymore. So that need for the perimeter heating, I hope, is going away.
So a lot of these are carryover from the previous code, but people are still catching on. In our code reviews, we see that. Basically, C403.7, you need to read it because it applies to a bunch of different building types. Like those building isolation dampers get missed all the time. 25,000 CFM, you start isolating by branch of the building, kind of, so you can have like that wing's open and that wing's closed, which is like dead nut simple and just good money. Like it saves a bunch of energy, but gets missed all the time. Kitchen hoods now have their own rules about what airflow is allowable, sort of an efficiency for kitchen hood. Most manufacturers will already beat it, but you got to know. Go looking for the mechanical engineers in the room. If you haven't been super familiar, you should get familiar.
Occupied standby. Just note that this is a big new thing in the code. It notices when a portion of the building has been unoccupied for 5 minutes or more, and it shuts down the ventilation to that space and sets back the temperature 1 degree. And you'd think that's not a big deal, but so you don't have that ventilation running anytime you're in that slightly larger dead band than you'd had before. And it turns out that saves a boatload of energy to not just be maintaining ideal conditions all the time that people are gone, and then rapidly comes back into the zone when people re-enter the space. I wanted to make it 2 degrees, but since and by the way, this is coming through ASHRAE and IECC in their next editions. It's already been voted in, so this will be a national standard, and maybe in the future we can go to 1.5 degrees or 2 degrees setback, but for now it's just the 1 and substantial savings. So just be aware that that's going to be part of your controls going forward. This is mostly unchanged from last code cycle. Just be aware that you've got heat recovery for certain buildings that have, especially if they got, they're running 24/7 and they've got lots of places to put that heat. that if you've got a steam system, that the condensate water needs to have heat recovery, and the same for a really large refrigeration system condenser, that you're going to take that heat and put it someplace where it's useful. And finally, you've got this heat recovery for space heating in particular. Once again, things with longer hours and places to put the heat. There's some rules to follow that you want to be aware of. This would be a really unfortunate thing to just have turn up at your final inspection.
Yes. So I want to drive home how weird most of the buildings are that fit in this section. So like for heat recovery for space heating, how many buildings are 70 hours per week, greater than 1500 MBH, high enough loads for the 0.45 CFM per square foot to really, to trigger cooling, and aren't already covered by a DOAS requirement. And I can come up, hospitals as well was the only one I could come up with, maybe if they're big, when they're big. The condenser heat recovery for refrigeration systems, that's clearly groceries, and it is something that new grocery stores are just going to do anyways, because it's like you're putting heat in and then you're pulling it right back out through the open refrigerated cases. They want that heat recovery, or it just kills them in the pocketbook. So most of these are things that are like, well, that makes a lot of sense. But like Duane said, if you miss them in that special occupancy, that special case, it's really cruddy to find out at your permit set. So be aware.
Ben and Duane have some questions. Well, Duane, first one's a quick one. I'm not sure what you said, but which equivalent ASHRAE 90.1 standard does the Washington 2021 code refer to, or maybe based on?
Well, remember that's only for energy modeling. Well, we have two standards. We have the 90.4 2022 version for data center cooling. For energy modeling, we use the Appendix G from the 2019 version of I'm pretty sure it's 2019 version of ASHRAE 90.1.
Thank you. And that one, and for either, does heat recovery refrigeration apply to cold storage warehouses, so beyond the grocery stores?
It has to have a place to reject the heat, so probably not by the letter of that section. You'd want to go read it and compare it against your specific project.
And if we're talking about the fruit storage warehouses we have, then I think we have an exemption in there for those in particular.
All right.
Heating the great outdoors. Just to be clear that if you have permanently installed outdoor heating, it's got to be radiant heating. It's not a space heating device, which some people have tried to use, so that it's radiating heat at your skin, and that's why you feel warmer, not because the air is warmer. We in Seattle expand this to include unheated spaces, and I'm always thinking of a place near my house that does tire changes for cars. So the garage doors are always open, and yet people working there in a really cold day need some kind of heat. So radiant heaters can be used there. It's got to be either turn off by a timer or by an occupancy sensor that's set for 20 minutes. And finally, you can do freeze protection for specific equipment and piping that is set so that it always shuts off when it's 40 degrees temperature. Another thing that that comes up is that we have fireplaces, fire pits, fire tables now, like and those have to be set so that they either shut off with a 1 hour timer that you can set and then have to reset after that, or if an occupancy sensor is used when nobody's been there, for 15 minutes. This particular photograph I took at a place on the Oregon coast where they just keep that burning whether there's anybody at the place or not, because it's like their trademark, but can't do that here.
So we have half an hour to cover 60 slides. We should do a very short break, or just go to the bathroom and make sure you use that mute button.
Let's just keep talking, and the people, yeah, I think we got a long ways to go, so let's go.
We do. So we got C406, 407, and some talk about refrigerants. So
all right,
stick
so
around.
I'll try to rattle through this. Here's our new energy requirements. Don't worry, where you used to have to get like 6, now you have to get 53. Those have been divided into smaller segments to make the point system work better. And note that you have you've got something that's required for energy efficiency credits, and then at the bottom you've got something required for load management credits, and those have to be fulfilled separately. But look at that, 53 credits for a group E. Well, here's Ben's look at it.
Yeah, I put in green the things I think you're most going to want to do. So take group E, you need 53 credits. Well, you sure are going to do high performance DOAS at 39 credits all of its own. You know, you get most of the way there. You'll consider 20% reduced lighting power for group E. That's probably a reachable thing. At 32 credits, you get done. So you only have to do 2 things. It's no longer points based. I gave you the things in yellow highlight are the crossouts by Seattle. So this is sort of both in one place. That's why I used it. Hit the next slide. I did not understand this the first several times through it. The load management measure, it doesn't count for the points up in the energy. It's got its own points it must meet. Some of these are relatively straightforward or relatively easy. The lighting load and HVAC load just do setbacks on what you probably already have control of anyways. Some of these are much less easy and really get into your design, like the thermal mass. Electric energy storage has been really interesting on a couple of our recent projects for separations and it gets into a thing some of the time, but it's all about a future where we limit demand at peak demand, you know, summer peak or winter peak, probably winter peak. We got to have the ability to dial it down so we don't do the California rolling brownout.
And yeah, there's a couple since that would get you about as much credit as you need for that group E there. So there are lots of options in there now that weren't there before. There's another credit for just better TSPR, so you can just say 5% or go all the way up to 20%, however you want, for better overall HVAC system performance. Another one, just want to be clear that for tenant spaces, if you've got credits for, if you're hooking up your tenant space to a central system that got certain credits, you're allowed to take credit for that. It's the way it was supposed to work since it's serving the tenant space.
So that is primarily our recommendation. This is a horrible old TI, but in a current code cycle, you get to stay in the current code cycle for 3 years. It's a while after.
It's 18 months after the C of O.
Okay. So could be years after the code cycle, but still within, yeah. It's an interesting thing. So that's a way to lock in your code cycle as long as you get tenants fast enough. But we really like the idea of having the building shell and systems deal with the overall so that the tenants don't have to come in and say, oh, but wait, we got to sign into your lease that whatever, your lighting has to be 20% less, you have to use point of use water heaters, whatever that a tenant might object to. The only caveat I'd have with that is that there's several that really heavily incentivize building air leakage. Remember, it's already a 0.25 CFM per square foot threshold, and it's tested towards the end of construction. So if you don't meet it, you're putting yourself in a points hole. So just realize what you're doing if you take those and the level of detailing you better have.
In Seattle, in case it wasn't obvious before, you can't use the you can't use fossil fuel equipment to get any of the C406 credits. Something about energy modeling that once again, Seattle will just be 10% below the building performance factor will be 10% lower than Washington State to reflect Seattle's more ambitious code and keep those together. And remember, this is all carbon emissions, not energy.
Yeah, so let's hit the next slide. It's important to note there's some notes on this. You can't get a whole bunch of credit from putting on-site solar. So you can't build a horrible building, but solar it up. Shall not be more than 3%. You have a change out of carbon from cost if you're already familiar with 90.1, 2016, and newer. This is straight out of Appendix G. It's Performance Cost Index. Let's hit the next slide. So that building performance factor isn't a straight like 40% multiplier. The next slide. There you go. There's the math. The PCI equals building performance factor times the regulated energy cost, and in this case, it's carbon. So that is like everything except process loads is regulated energy. So the unregulated loads, the process energy, kind of sit to the side on the calculation. And you're comparing against a 2004 ASHRAE 90.1 baseline. There's a whole backstory to that we don't have time for. And the building performance factor is pretty stringent. So like look at a restaurant, you need to hit 0.32 of the regulated energy cost, and that's on you know, a whole chart from ASHRAE. You model both of them. It's a real pain, and it doesn't get you a lot of window area. Hit the next slide. It's got those same carbon multipliers that we talked about before, where electric resistance worse, heat pumps always win, but they also have a UA backstop. So U factor times area. This is straight out of the last session, that you only get to go so far a percentage beyond 20% for Washington, 0% for Seattle, UA extra. So that's a long way of saying if you want the most window area you can get in Seattle, you really should look at some of those high performance glazing options, because they'll get you a lot more window in almost every case than the energy model method will get you. And in Washington State, maybe it's a trade-off, but for the cost and difficulty of doing an energy model, unless you're one of the ones that already got 40%, so not one of the ones in this list, then you probably want to go back and do the prescriptive path. All right. So how hard is it? It's not much fun. It's 100 hours of engineering time. I'm going to tell the truth. And then the next slide, why do it? And I don't have a great answer to this, and that bothers me because I run an energy modeling group. But I don't have a great answer why you're going to do this for energy code. Maybe you're a super high performance building and you're not worried about passing this harder than prescriptive path threshold. Or maybe you are already doing LEED v4.1, so you're already modeling an Appendix G from 2016, so you get a different building performance factor and the math is easy. You don't have to do another model if you're already doing LEED. That was kind of those are the two that I came up with. Duane, do you have other people coming in with energy models for other reasons?
We don't get as many energy models as we used to. That's somewhat by design. You've heard me say this before, but the primary reason that energy modeling was done to start with was to find a legal pathway to have worse building envelopes. And people were able to make their building envelopes U values worse by dramatic amounts. And so we wanted to maintain our building envelopes so we don't allow modeling to be used to make the building in Seattle any more than 10% worse than prescriptive code. And we've really clamped down on some things. Also, the new 90.1 Appendix G method doesn't allow for as much monkey business as happened in our old modeling methods. So model if you want to, but don't use it. Don't hope that you can use it to make a worse performing building.
Yeah, and monkey business, he means perfectly allowable by the method, although questionable from an energy modeling standpoint.
Yeah, questionable is the polite term. You gotta commission your HVAC system and provide all these plans and supports. And by the way, we have there's been some changes in management around here, and it's going to be much more vigorously enforced. So do to it, and also see below that picture of the finish line there. Notice that there are, I said POS, post-occupancy commissioning requirements that are significant to make sure that everybody does in fact finish up all those, correcting all those issues that turned up during the commissioning.
So my note is certified commissioning professional. I'm one of those. There's many of them in town since this has been in the code 2 cycles now. There's a fair number of them in Washington State because it's been in the code cycle for 2 cycles now. And the line is 20 tons, and that's building capacity. Go read the code. It's not each system. People try and run that loophole. It's 20 tons. So pretty small building.
Duane, we have some curious humans out here asking if you're seeing a trend of more people going prescriptive with the 2021 code rather than energy model way.
We don't know about the 2021 code yet, since nobody has
right.
But for the 2018 code, there was a reduction. Like I said, we get about 1 per month, and they have other reasons. Typically, usually it's they're going for a zoning bonus that requires energy modeling.
Thank you.
All right. There's a system by which you can get some credit in modeling for high performing unregulated system, and the idea is that if you have such an idea, send it to us with documentation that shows that it's actually better than what is typical construction, not just something everybody's doing anyway. And if we approve, then we'll list it publicly and say, okay, everyone can use this. There's pre-approved. We have a few residential appliances that if you do the high performing version and they're actually installed in your apartment building before the final inspection, you can get credit for those. People have been asking me about FTD systems, heat tracing, point of use water heaters. That and my answer has been, yeah, maybe just submit the idea, and if we think it's legit, we'll post it, and then everybody can use that as credit for doing something better than code that's not actually in the code. Remember, you still got to do energy modeling, metering. I don't care about the meters. I want to make sure that everybody has an actionable energy display, and this is also required if you're doing a major replacement of your HVAC system.
Yeah, for the HVAC equipment you're replacing above certain size capacities. From a commissioning standpoint, these meters are golden. They give us so much more data about how it's performing and seasonally performing than we get just from reading, like, are you meeting the set point on trend log? It's great. So they're fantastic for that. They're fantastic for owners, for knowing long-term, did I get what I paid for?
In general, alterations, you can leave stuff that was built, if it was built legally back in 1948 or whatever, you can pretty much leave it forever. With not many exceptions. New stuff has to meet code, and where we have substantial alterations or change of occupancy or change of space conditioning, then it becomes more like very close to the requirements for new buildings. We going through this time, we're trying to say what are we going to do with existing buildings that perform poorly. We have some precedent. I show in one of the bullets up there that we required nightclubs to get sprinklered. We required some safety things on egress stairs and high rises, but the building performance standards are a pretty novel thing, and it is only for those kind of jurisdictions that really are serious about it. So when you're replacing existing gas or actually existing electric resistance equipment, it's going to be expensive to go to heat pump. the most economical time would be that right when you're doing a replacement anyway, right? So right now we say, yeah, you have to do it, and there's an exception for one-off for replacing one item of failing equipment. That was subject to some abuse. So new code would be, there's more options to postpone, but no option to just keep replacing gas equipment forever. The state has a building performance standard system, and I'm just going to run over this really quickly. That's based on energy. Those energy targets were set at what they thought was average for each of the various kinds of buildings, and might be set lower in future legislative years. But for right now, if your building is performing worse than average, then you're going to have to bring it up to that in the next decade or so. In Seattle, we're looking at building on top of that and controlling emissions, and so there's like, it steps down every 5 years till in the 2040s it'll will be at zero carbon for existing buildings. If you look at this, those blue stripes are the Washington Building Performance Standards compliance years. That, by the way, they would also accept that you could have a plan submitted and prove that you make annual progress on that plan, which could push you out several years further, but might come down. Those red lines, dotted line being multifamily and solid line being commercial, show how we're requiring in Seattle the building emissions performance standard to step down to zero sometime in the 2040s. So basically, what we got now is that if you're one of those building types on the left, affordable housing or hospital or whatever, or you have a really expensive electric service, you could be exempt if you do a future decarbonization plan. If you're some other kind of building, you're allowed to keep 50% of your existing gas capacity and submit that future plan. If there's an emergency, you could replace as much of your existing heating with gas as you want, but you're typically going to have to post a bond that says within 4 years you're going to get that 50% heat pump capacity. Ben?
So this is the same list as chapter 4 because all of those apply. And you get a couple more, the most important ones being where triggering an unplanned electrical upgrade, you can talk about keeping fossil fuel. Let's go to the next slide. There's a whole table in here that I thought was just a graphical representation of the list. It's not. There's other things in there for Washington. And it took 3 readings and one of the other principals in our firm pointing it out for me to go, oh, you do get to keep your boiler in that case in Washington. In Seattle, a lot of those are crossed out. Let's go to the next slide. Seattle, again, adds exceptions for very small buildings and for some of the things that we really need help with, like affordable housing. So I thought it was interesting, again, that in Seattle, you actually get more exceptions, but you're also going to do a future decarbonization plan it's a little documentation heavy. You need to have a plan for how to go to a heat pump in a relatively near future.
So comparing the building emissions performance standards and the code, you could see there's those 2 same red lines sloping down over time that you're going to have to deal with. But let's say that in 2028 you have to replace your space heating heat pump, you could replace 50% of that and keep the other half gas. Maybe in 2032 you got to replace your water heater as well. You could do half of that, and then those heat pumps will probably last 15-ish years. So you can start to make decisions on whether, like in this case, if it's a commercial building, if it's not multifamily, then maybe you're going to want to replace with heat pump to begin with anyway, because you're going to have to otherwise replace that before the end of the equipment life, whereas not with the multifamily. But here's actually more realistic. Because of dramatic oversizing by engineers of the existing systems, it might be that you, by the time you replace 50% of your existing gas water heating capacity, you've actually got 100% of all the that you need. So it might be that replacing up front is a smarter idea. There's a quiz we'll get in 2 slides. Like, what factor do you think that mechanical systems are oversized? You got 10, 20, 50, 100? What would you say? Costs are real. This was a study that was done by Mac Miller a couple of months ago, and you can see that as you need to get more EUI reductions, the cost per square foot it is going up. Now, this is a partial answer to that quiz there. This is for water heating systems, and Appendix A, the red dots. This is for two dozen real world buildings. The Appendix A shows how big the system would have to be designed to be. Appendix M, the new one for buildings with low flow fixtures, shows how much you would have to do if you're taking advantage of those low fixtures, much less. But those black dots at the bottom are the actual peak flow rates measured over the course of a year for any of those buildings. So with the traditional system you've been using to design your water heating system for multifamily, you've been oversizing by 10 or 12 times what the peak will ever be for your building. And with this new Appendix M, well, you're only oversizing by 2 or 3 or 4 times what it will ever be in the peak. So the cool thing is that replacing the whole system, like at that Appendix A or even the Appendix M level, looks dauntingly expensive. It might be that you can replace it with a system 1/10 of the size, not have to upgrade your electric system, and do just fine. So go and measure how your building's really performing. That future decarbonization plan that I kept talking about, that everybody will have to do, that's going to be an engineered schematic design and cost estimate, right? And you're going to have diagrams, you're going to have plans that show where all the equipment goes, and all the other things you're going to have to do for air handling, for structural, and a real world cost estimate. Along with that very last one, some recognition of when the Washington or Seattle performance standards is going to kick in and require you to do this anyway. I figure that, if design is 10% of construction cost and schematic is 10% of the design cost, we're talking like 1% of the cost of really doing it, but this will get you started along the path. If you're worried about the relationship of these building performance standards to code, look on the far right. The building performance standards for a mid-rise office is in the 60s. Current Seattle code probably gets you a building that has an EUI in around 30 and heading downwards. And those 2 highlighted numbers there are mid-rise offices in Seattle that are functioning well below that 2030 target already. So not to worry. So the building emissions performance standards for Seattle says you have to do certain date for decarbonization. The code says you got to do heat pump as you're replacing, with some options to not do it yet, but you can either decide to postpone or not based upon the construction cost, which is money up front, which owners just hate to pay, or when you got an upgrade required, which might come before the end of that useful life of that equipment. So you decide. Cooling system alterations, just remember that you got to upgrade to DOAS if you're adding cooling to a building. However, if you're just going from gas to heat pump, we'll consider that is not a change in space conditioning and will not make you upgrade the rest of the building. So sorry about all the type here. We're hustling through this last few minutes of the presentation, but if you're replacing an air-cooled chiller, you're going to replace it with a heat pump system. And there's those, you saw from my charts from before, there's certain building types that are exempt and certain system types that are exempt. And did you want to, let's just skip past that for a sec. If you're replacing your heating system in Seattle, once again, Same thing, you're going to replace it with a heat pump system or take advantage of one of those sets of options to postpone that replacement. And yeah, subalts,
Yeah.
you want to say a word about subalts?
So if you're just adding cooling or you're a change of occupancy or your substantial alteration, Seattle specifically, you trigger a whole bunch of stuff. Go have that pre-submittal conference that is required. Sometimes it's by way of email instead of actual meeting, but go do it every time. If you're replacing 2 of any systems, you need to go have that conversation.
Hey, refrigerants. We're gonna just be aware that for space heating equipment, for HVAC equipment, the old HFCs are gone. And remember, these dates are for when the equipment is manufactured, which is typically a few months before it's installed, not for the permit date itself. So for anything that's in design right now, you're probably into those new requirements.
Yeah, so chillers start in 2024. Heat pumps start in 2025. We sure have designs that are not going to build until after that. So our standby R410A doesn't really work anymore. So it's got a global warming potential of 1890 or over 2000. It depends on your baseline, 30-year or 50-year. Next slide. We need refrigerants for the refrigeration cycle. They are the thing that makes the magic of 300 to 400% efficient with air source systems work. And it works by phase change. So we need these special things that are long-lived that do phase changes over and over and over and over again without breaking down. Next slide. R410A is great. We have good equipment. This is indexed against R410A. So you either give up efficiency or you give up volume, so your compressors get weirder and weirder, or you move from non-flammable to slightly flammable. The orange dots are highly flammable, the red triangles. So our most likely heir apparents for refrigerants are R32, which code doesn't really recognize yet as a lightly flammable. We don't have a distinction between lightly flammable and really combustible gas. Or the 1234, some of the different azeotropes of those. So it's going to be interesting times as manufacturers go to these. CO2 is the obvious other one with a global warming potential of 1, the lowest that is out there for refrigerants. So stay tuned, it's exciting.
State law does recognize those mildly flammable, do they call them, like R32?
It does.
H2L, and so it is allowable. It's just that not a lot of equipment's yet available with that refrigerant.
Right, and it's going to start coming with things like this equipment must be installed in a room bigger than X. You know, it's that sort of level of detail. Here's your refrigerants, and way off to the left is the pressure. That R744 is CO2, so that's the big hindrance to CO2. I think it's going to be a long time before we see CO2-based field joint systems. It may never happen because it's such high pressure. But all the other ones, we can get there. Last slide. This is a graphical representation. This is why we're doing it. So R410A down to R32 is a great reduction. If we go most things to CO2, that's even better. And ASHRAE tells us on a carbon estimating, global warming potential estimating standpoint, we should plan for 0.2% leakage from refrigeration systems every year. Doesn't sound like a huge amount, but it kind of works out that over the life of the system, every system is going to leak some.
Yeah, 50% of all refrigerants utilized worldwide end up in the atmosphere. So yep. A lot.
A lot. Last thing to say, as long as manufacturers are on board for these deadlines, and we already have, our reps are in our office talking about new refrigerants, and we're asking the questions for longer construction windows, it's going to be fine. This is going to be like every other refrigerant. I've now gone through 3 refrigerant phase outs in my career. So this is just another one.
Yep. So thank you all so much. We're just about at the top of the hour. Wanted to mention that we got a few more of these coming up. including one just next week on water heating, and then week after that on alterations. So hope to see you in the next cycle of talks. You can get in touch with us and get in touch with the Lighting Design Lab as with any further questions you got. You want to make the last word here, Armando?
You're muted.
Maybe not. There's a
hope to see you on the next one, right?
yeah. You'll see a survey pop up as you close out, and feel free to say wonderful things about us. See you next time. Bye.
Duane, pleasure as always. Thank you.